Hello. In this video, we're going to study the BJT differential amplifier with an active load. As we have seen, we can use an active load, which is basically a current mirror, connected to replace the collector resistors, in this case in our differential amplifier. And the advantage that we're going to gain out of it, we're going to get several advantages, but one of them is higher gain. Because as we have seen, the gain is proportional, the differential gain, to the overall resistance connected to the collector. And the resistance connected to the collector, now it's going to be the resistance looking into the collector of our transistors for our current mirror. So it's going to be in the order of little RO, so a very high output resistance, very high collector resistance, which is going to lead to higher differential gain. Let's go ahead and take a look at the circuit and study what the differential gain will be in this case. Again, what I have done is replace my collector resistors with the following block, which is my active load, comprised of transistors Q3 and Q4. In this case, I have used a basic mirror. All right. So advantages of this circuit, this configuration. For one thing, I have gotten rid of two resistors and replaced them with transistors, and therefore it's a better design for integrated circuits. So replacing RCs with transistors. Good for IC design. Transistors will occupy less space than the corresponding collector resistors. We have also increased our output resistance for the circuit. That will be the resistance looking into the output terminal out, and that's going to be equal to, in the previous case, if you remember, when we had the collector resistors, was RC in parallel with the little arrow of transistor Q2. In this case, it's going to be the little arrow of Q4 in parallel with the little arrow of Q2. And finally, we have increased our differential gain. So our AD is approximately equal, and we have seen overall resistance connected to the collector divided by the overall resistance connected to the emitter, 1/2 of that, because this is a single-ended output. And so it's going to be, in this case, out 4 parallel with out 2 divided by 2 little RE plus RE. And we can see that we're going to be able to achieve very high gains, especially as our capital RE goes to 0. So maximum AD max happens when RE is equal to 0, and it is equal to, or approximately equal to, R out 4 in parallel with R out 2 divided by 2 little RE, or 1/2 1 over little RE is equal to GM, the transconductance of the transistors, so 1/2 of GM, R out 4 in parallel with R out 2. And we can see both GM and little RO are going to depend on the collector current, so this is going to be a ratio of the early voltage divided by 2 times the VT. So maybe perhaps express it like that. It's going to be 1/2 of GM out divided by 2. approximating both of them to be equal to each other. And this is going to be equal to 1/4 of VA divided by VT. So early voltage typically a very high quantity in the range of hundreds of volts, VT a very small quantity in the range of millivolts. You can see the gain is going to be a very large value. Now normally we're not going to want to design amplifiers with that large of a gain. Notice that even though it is a very large value, we have little control over it because both the early voltage, the thermal voltage are going to be parameters that we don't have a lot of control over. They are going to vary with process variation, they're going to vary with temperature, etc. But the idea is we want an amplifier with a very high gain, and then we're going to be using negative feedback. You're probably familiar with how you connect your op-amp. It is an amplifier with a very high gain, the order of 10 to the 6 volts per volt, but then you connect it using negative feedback, you reduce the gain, and you basically expand your linear range. So there are going to be advantages to having an amplifier with that large of a gain, and then connecting it using negative feedback. One more thing to mention. In here I've used my basic mirror as an active load. We could have chosen something like the base compensated mirror, for example, which will give us a more accurate current transfer ratio, thus making the currents more equal on both branches. And as we know, this circuit relies heavily on good matching. So, for example, you might be able, or you might encounter this circuit in a similar form, but with a different type of mirror, let's say a base compensated mirror, for example. And it will be, the workings will be exactly identical. In here we have made the assumptions that the currents flowing through both branches are equal to each other. But obviously if you have a current mirror with a better current transfer ratio, then you're going to run into less offset problems due to mismatches. One more thing to mention is that in this circuit we don't have a load connected, but if we were to connect a load resistor, let's say over there, our effective gain will be reduced. So our effective differential gain, let's say with RL connected, will be approximately equal to RL4 in parallel with RL2 in parallel with RL, because that now forms part of the overall resistance connected to that collector node, divided by 2 times little re plus Re. So we'll basically have to take that into consideration. One more thing to mention is how to calculate frequency response for this type of circuit. And it is no different than the calculations for the frequency response that we did for common emitter, common collector, etc. Let's imagine, for example, that we wanted to take our output through a coupling capacitor. So imagine I wanted to recenter my output at 0 volts. I might put a coupling capacitor. I'm going to call it C out. Or actually, I call it CC out so that we know it's a coupling capacitor. Yeah, let's imagine that my signals of interest are going to be up to 1 kilohertz, for example. So I want, or higher than 1 kilohertz. So I want my low cutoff frequency to be set to something lower than 1 kilohertz. Let's imagine 100 hertz, for example. The way I will calculate my CC out, so for the frequency response, as selecting coupling capacitors. In this case, I will have my low cutoff frequency as set by CCO will be equal to, and the coupling capacitor CCO forms a high-pass filter with the Thevenin resistance connected across its terminals. So it's going to be the cutoff frequency for a first-order high-pass filter, 1 over 2 pi R Thevenin times CCO, R Thevenin connected to CCO. In this case, it's going to be the series combination of RL and the resistance looking into the transistor Q4 in parallel with the resistance looking into the collector of Q2. So it's going to be 1 over 2 pi. It's going to be, the R, 1 over 2 pi, the R out of my circuits, which we have seen it's the parallel combination of R4 and R2 plus RL times CCO. And again, if I wanted to set my low cutoff frequency to something like 100 Hertz, then I will just have to make that substitution into this equation and figure out the value of CCO to achieve that low cutoff frequency. And I think that's it. Thank you.